Greetings. This presentation is entitled Forces, Moments, and Equilibrium. In it, I'm going to discuss forces on bodies or structures. This course will focus on building structures. A body is just basically anything. It could be a column or a beam. In our case, it's really anything to which a force is applied. We're going to talk about different ways to measure forces. When forces are applied to columns or beams, for instance, internal forces are produced within the structural members. We're going to discuss them as well. Moments are also produced within a structural member, within a beam. We will discuss what those are. The very important concept of equilibrium. So when the column, the beam, the body, or the individual structural member, or the entire structural member as a whole is at balance and in equilibrium, very important. And forces at supports. So if a pair of columns is holding up a beam, what exactly happens at the interface of those two structural members? Okay, so starting at the very top, we're going to discuss the study of statics, which is in the branch of mechanics. So it's concerned with the analysis of loads. So loads are those external forces that are weighing down on an object, pressing on an object, and also it creates moments, which as we said, we're going to discuss. So torque, so kind of a tendency to rotate in a beam. So that is what statics is looking at, and very importantly, it is looking at them in the state of equilibrium. So this is to say that all the forces kind of net out to zero, everything is equal, and typically for buildings that means nothing is moving. The building is pushing down on the earth is pushing back with the same equal amount of weight, and nothing is moving, and that is equilibrium. Everything is kind of washes out in terms of algebra, in terms of math. We will talk more about that. So this is based on Newton's first law, so it applies to external forces. So something is pressing, so the wind is pressing on the side of a building. The building is pressing on the earth, for instance. So those are external forces. So one object is pushing on another, as opposed to something happening internally. So an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted on by an unbalanced force. So we've heard this. So this situation implies that the net forces on every body in the system is zero. So this is the big conclusion, basically, and it goes back to the principle of equilibrium, that whatever force the building is pushing down on the earth is pushing back with that same amount of force. So it's whatever, let's just say it's 100 pounds down, and then it's 100 pounds back up, and that all nets out to zero, and that's what says we are in equilibrium. Okay, so that is the most fundamental level what we're discussing about. For it to be the study of statics, it must be in equilibrium, and for us in the world of buildings, that means that they are at rest. Okay, so here's equilibrium. The sum of all forces in the x, y, and z direction is zero. Okay, so here is our grid. So we have x is our horizontal typically, y is our vertical typically, and z is actually I'm discussing this in terms of like CAD and Revit, how we describe this axis. Z is the third dimension, is the way we typically describe it. So here's a beam, for instance. So in the world that we're talking now, x is the vertical direction, y is the horizontal direction, and z would be that third dimension, which in this case it actually doesn't really apply. So in introductory statics, it only considers coplanar forces, thereby eliminating the z-axis. Okay, so what that means is when engineers are looking at this beam, they are only looking at it in the up and down, the y direction. That would be the x is our horizontal direction. So here we have a force P coming down in the y direction, and then we have two reactions pushing back up. So that's all in one direction, the vertical direction. In the horizontal direction, there are no arrows indicating that anything is pushing this beam left or right. So And then we also have the sum of moments, which we're going to discuss shortly. So in order to have equilibrium, the conclusion is, so this is the sigma sign, sum of forces in the x direction equals 0. Okay, so it's the sum of forces in the x direction equals 0. So anything pushing in the x direction is being met with equal forces. Anything being pushed in the y direction is also being equal. So this P is equal to the sum of these two R's. So this is pushing down with 100 pounds, and this is pushing up, being that everything is symmetrical. We would know that this is pushing up with 50, and this is pushing up with 50. And that's how we get to equilibrium. The sum of the forces equal. And that's in our one direction, the vertical direction. And then the sum of moments as well. Okay? And this just again says that we don't care about the third dimension. We're just looking up and down, left and right, and then moments is a special circumstance we'll talk about momentarily. Okay, so when a load is applied to a structural member, an internal force is created. All right, so here's this little diagram right here of a rubber band being pulled on. So the external force is being produced by the hands. The hands are kind of grabbing the rubber band and pulling it. That's where our external force is occurring. But then something is happening within the rubber band, and that is tension being created. So the internal force that develops inside elastic due to pulling is tension. Okay, we'll talk more in a moment. Next slide about what tension is and compression and those different internal forces, but that's what it means. We have something happening externally, but then something occurs internally. Forces influence objects to undergo a certain change, either in its movement, direction, or geometry. All right, so if we go back very quickly to the object at rest stays at rest, and the object in motion stays at motion. So that is the motion, basically. If something is rolling, it's just going to continue to roll until something pushes back on it, essentially. That's not, for buildings, that is not our concern. We typically don't discuss movement. It's really geometry. So that is when a beam gets too much force applied to it and it bends, basically, when something deforms. So that's geometry is mostly what we're concerned about with. In forces, just in more broader physics terms, you'll hear movement and direction discussed a lot, but for buildings, it's geometry. Okay, so here we have a book sitting down on a table, and it is pushing down, and then the table is pushing back up. Okay, so that's kind of actions and reactions applying, and that's what we have happening here. So maybe we have a state of equilibrium where nothing is happening inside this rope. Just like the rubber band, there's tension being created in there. But to go back to our previous discussion of equilibrium, if neither of these people are moving, then he's pulling with 50 pounds, he's pulling with 50 pounds, and it nets out to 0. Okay, so that could be an example of equilibrium there. All right, so now what happens inside of structural members when they get weighted? Okay, so here we're going to discuss compression, an internal force that causes structural members to shorten and can result in failure due to crushing. All right, so when we discuss some forces, we're going to discuss them with arrows, and it's very, very important that if you're asked in a quiz to identify or to draw, that you place arrows correctly. So 2 arrows in line with each other, facing each other, is compression. All right, so this arrow, something is pushing in this direction, something is pushing in this direction, and this thing is getting crushed. And we see some examples of how wood crushes. So all these little lines of the crushing of the wood, that's just different ways relative to the wood grain. We're not concerned about wood just yet. We'll have plenty of time to study wood later. So that is not relevant in this first presentation, is what exactly is happening to the wood grain and the different ways in which it crushes. That's not the big point. All we care about is the compression, crushing. All right, here's tension. So 2 arrows going in the opposite direction. Something is being pulled apart. The force that causes elongation or lengthening of a member. So this is tensile failure right here. So this is the strut at the bottom of a bridge, kind of a beam. And it often happens when fasteners are added, it becomes a weak spot. So there's a big hole drilled through this beam, and then it has been pulled apart. You can see that separation has occurred right at that spot, which was weakened, and that is tension. And we have 2 arrows pointing opposite directions. Same happened here. This whole piece was pulled in tension, and that's why that split occurred. So again, relative to the wood grain, different ways the wood could fail. That's beyond our concern at this point. Okay, shear, another internal force, the combination of two forces acting in opposition to each other, resulting in a sliding or tearing tendency. Okay, so this is a diagram of wood plates and steel plates. The specifics we don't care about so much, but what we have going on is here's a piece of wood being pulled in that direction. Here it's flanked by these two that are being pulled in that direction. And these fasteners right here, which are nails in both cases, are experiencing shear. Part of them is being pulled in one direction, parts being pulled in the other, and the fasteners are being sheared. This just goes to show that in a wood plate, the fastener would kind of be nicely, just kind of bent more kind of gradually. Where in a steel plate, that's not afforded, that nice bending, and right really at where the connection takes place, that interface, it's going to be a more sharp kind of shearing action. Okay, but that again, the specifics we're not so interested in. And then finally, we've covered compression, tension, and shear, and now we're on to flexure, or bending. So this is a specific force that beams experience. So the material on the top of the beam is being compressed, while the material on the bottom is being stretched. So flexure experiences two of these things, actually, in combination. Compression and tension are both being experienced within a beam. So here, the dashed or dotted line right here, that is the original beam. And then we have a load that's applied to the beam, and that's what we see happening there. There's our beam, and there's the load coming down. And what happens is the top is being pushed together and being compressed, and the fibers actually at the top of a wood beam, or really kind of any beam, we wouldn't call them fibers necessarily, but the internal layers or molecules are actually being pushed together, and that top of the beam is actually shorter than it was initially. And then the bottom, it actually gets longer. And in certain types of material, which we'll see some images of later, we could actually see if you have like a beam, this looks like a solid piece of wood, but if you have a beam that's built up of numerous plies, like a piece of plywood, you could actually see this happening. You could see the failure occurring between the plies, and you could see them pushing past each other. So shorter at the top, wider at the bottom, compression, two arrows facing each other at the top, tension, two arrows facing each other at the bottom. Maximum tension is right down here at the bottom. Maximum compression is right here at the top. And then as we go deeper into the beam, the compression lets up and the tension lets up, and then you have this point right in the middle, neutral axis, where nothing is happening. We will talk more about that. Okay, so that is flexure. That is our fourth, and then we have one more. Fifth is tension, our fifth internal force. So the force that results in a twisting action on a member. Okay, so here, this diagram, it appears, or I believe, that this would be pinned in one spot essentially, or it's being pushed in the opposite direction, and this one is being pushed in counterclockwise. If we were looking at it from this direction, this one's coming counterclockwise, this one's coming clockwise, and then the orientation or the axis is getting twisted. And you can see that in these old pictures, which are pretty nice. So this is actually hickory, it says here, black hickory. Hickory is what we make baseball bats out of, so super tough. It's only in the toughest materials that the full effect of this action can be observed. Brittle woods will snap off suddenly with only a small amount of torsion. So the twisting occurs. So it's basically a soft or a brittle wood that snaps easily would just be broken, and there would be no evidence. We'd have a broken branch, but no telling of exactly how it got loaded. Did it get twisted, or did it get loaded like a beam or crushed like a column? Here, there leaves nothing to the imagination. These things have clearly been twisted, and they are suffered from torsion. Okay, moving on. Identifying an external force. So when an external force is pushing on something, there are a couple different ways in which we describe it. Okay. So it has a magnitude, or the amount of force. So here's a wheel, and it is being pulled in this direction by a force of 10 newtons. Okay, so it's typically measured in newtons or pounds or tons. Well, I stick typically with pounds and tons just for consistency, or they are measured in newtons as well. And then larger forces. So in the world of buildings, you will hear a lot about newtons and kilonewtons actually. Okay, so that when buildings get that big, they just lop off a bunch of zeros. So 10 to the third newtons that would be. So 1,000 newtons there. And then this is just describing, so the magnitude. So this is just kind of a graphic of how a force is often drawn. So this 10 newtons pulling in that direction is described by this arrow, and the length of that arrow is the magnitude. That's just a convention for drawing it. They also have a direction of the force, which refers to the orientation of its path, called its line of action. All right, so direction is usually described by an angle the line of action makes with some general reference such as horizontal or vertical. So here we have an eye hook that's been mounted to a wall or something, and it has two pieces of rope pulling on it. And this is like classic kind of statics and trigonometry problems. This is very much what they look like. So something is pulling with a certain force T here, something is pulling with 8 kilonewtons in this direction, and it's going back to the direction of the force. This one is 45 degrees south of the x-axis. This one could be in the positive direction, if we call clockwise a positive direction, some given angle off of the y direction. So that's the description of the direction of the force relative to something else, so relative to the x or y direction. Yeah, and we'll talk a little bit about this quickly. And sometimes when solving these trigonometry problems, these statics problems, it's easiest to take one angled force, such as we have here, the dog's chain and collar, and just break it up and turn it into two simple forces. And this could allow the math to be easier, to figure out the actual magnitude of this, perhaps, is what we need to figure out, for instance. So sometimes the math is more simple if we work with things on the x and y axis, as opposed to diagonals. Okay, so that's common ideas behind statics and solving these problems. And then they also have a sense. The forces also have a sense. So refers to the manner in which it acts along a line of action, up or down, left or right. So basically we've established that there are these lines. So we have these lines, and the next step is to put the arrows on them and talk about which direction they're actually heading. I often make the example of saying that, like a road like Broad Street, for instance, runs north and south, but at certain parts it's only north-facing traffic, and certain parts it might only be south-facing traffic. So the road runs north and south, but then we have to be more specific and talk about which way the traffic runs, and that's what this is saying. So it's going to be positive or negative, and so this is just something that's set up before you do the math, and you just say that everything up is positive, everything that's down is negative, everything that's right is positive, or vice versa, as long as you're consistent with your senses. So everything that goes clockwise is positive if we're talking about moments and rotation. Everything that goes counterclockwise is negative. So again, if you're consistent with your rules, it doesn't matter which is positive and which is negative. As long as you're consistent in how they're applied, then everything, again, going back to that very first slide, everything nets out to 0. We have 100 going down, 100 going up, and the answer is 0. 100 going this way, 100 going that way, and the math equals out to 0. All right, so that's the sense, the direction, and that's how it manifests itself in equations. This goes back to the dog leash. So two forces are replaced by a single force. All right. So if we have a horizontal and a vertical, then the resultant is the combination of the two. Okay. So the single is the resultant, and it is equal to the same of if we solve these as two separate individual forces, we'd come up with the same answer here. When we apply magnitude and direction and sense of force to them, and we do undertake statics, basically. We undertake an evaluation of the forces, which goes back to statics. All right, and so this is a tiny bit of math just to understand the things that we were just talking about. So forces sum to a resultant force. So if the forces are the same, they add up. If the forces are the opposite, they subtract. In the reverse, a single force can be replaced by two forces. They are called the components. So right here, we have two forces. The red, this one's being pushed 3 newtons from left to right. This one is 4 newtons from left to right. And the resultant, if we were doing the math, would be 7 newtons left to right. All right, so being that these two are moving in the same direction, we add them up. Now we have two that are going in opposite directions. We have a force that's pushing with 3 newtons to the right, and we have one that is going 4 newtons from right to left. And now the result is we add these up and we get the 4 minus the 3 is the 1 from left to right. Okay? And then this is going back to the dog's collar one more time, and this is based on the 3-4 triangle. So we would just this 4 would just belong up here. So we're just taking, and that's the trigonometry of it, is basically working with triangulation and angles and lengths of the triangle sides, and determining that if this 4 were up here, we'd have a 3, 4, 5 triangle. The 3 and the 4 could easily be replaced with the 5, or vice versa. Okay, we're not going to be digging into any difficult or complicated math, but I just want you to understand these principles behind it. Okay, so let's just take a look at a problem here, work out the resultant forces, and state the direction. So here we have 25 going from left to right, and here we have 20 also going from left to right. So they're going in the same direction. So I'm going to say 25 plus 20 is 45 from left to right. Here we have 25 going from left to right again. Here, however, we have 20 coming from the right to the left. So this one is the greater number. So I'm going to say that the answer is 5 from left to right. So that is all correct. Okay. So yes, this talks about unbalanced forces, going back to that very early slide. If one force is greater than another, something's going to win out, and we will not have that state of equilibrium that we are always looking for. Okay, let's move on to moments. Very important. So, a moment, or torque, those are two synonymous words there, of a force is a measure of its tendency to cause a body to rotate about a specific point. So a tendency to cause a body to rotate. So it's not necessarily rotating, but it's having a tendency to cause. In order for a moment to develop, the force must act on a body in such a manner that the body would begin to twist. This is different from a tendency for a body to move in the direction of a force. So it's not being pushed, it's twisting about a point. So here is a knee and a foot, and if this is weighted, if this foot were stretched out and weighted, there would be a tendency of it to rotate about the knee. Okay, and depending on this distance right here, that would influence the magnitude of that moment, how far away that weight is. Is it weighted right here at mid-calf, or is it weighted down here at the ankle? That makes a difference. And here we see it in a column. So right here we see a force moving through a floor directly through the column. Here, however, the force is off to the side, and that lever arm is that direction. So now that force has to come down, and now it has to take this path over here to get to the column, and then it comes down. All right, so a detour. All right, so a moment occurs every time a force is applied so that it does not pass through that center point. Okay, it is due to the force not having an equal or opposite force directly along its line of action. So we talked about the line of action. That is the line of action, and these forces are in line. All right, here's the line of action, but now the force is not on it. It is off to the side. Okay. All right, the elements of a force. So it has magnitude. The magnitude of the moment. I'm sorry, the elements of a moment, not a force. I believe I said that. Magnitude of a moment defined by the product of the force F and the moment arm. Okay, so here the moment of the force is defined by the force, the magnitude of it, and the distance. Okay, so this distance is a critical part of the equation to figure out how big this moment is. All right, so the moment arm, or the lever arm, is a perpendicular distance between the line of action. All right, so the perpendicular distance is right there. All right, so this moment that is occurring, so this is a beam right here, and we have a force here, and it is making a tendency for this beam to spin around, to rotate right here. It's pushing down. This part's going to go up like a seesaw. And that moment, that's the tendency of this thing to rotate. And then we want to figure out how big is that moment. And that is a function of how big that force is plus how big that detour is. All right, so that's what that is. The magnitude of that force, the length of that distance or detour tells us how big that tendency to turn is. All right. So a moment is expressed in foot-pounds. So this is basic physics here. So the amount of energy, basically, that it takes to lift a 1 pound weight 1 foot off the ground. That is a foot-pound. That is just a standard in the world of physics. Okay. So that's how moments are expressed. 1 foot-pound, the torque created by 1 pound of force acting at a perpendicular distance of 1 foot from a pivot point. Okay, so these are two different things here. This one just describes what a foot-pound is, and now this one is applying it to a situation that involves torque. Right. So what this is right here, this gadget, this is a mechanics wrench, essentially a torque wrench they call it. So here is a screw or a bolt that needs to be tightened, and this is a handle. So we put our hand right on here. This is the handle. This is the handle, and we are going to push. We're going to twist it. We're going to twist it. We're going to take this thing and rotate it in this direction to tighten up that nut. And what's going to register right here on this digital one, or right here on this scale, is how many foot-pounds have been applied to that bolt. And manufacturers will often specify, they'll say, tighten this to a torque or a foot-pound rating of so many foot-pounds. And at that point, the whoever's fabricating or building whatever is being built would take out their torque wrench and tighten up all the bolts to that number. Okay, so that is a foot-pound of torque. So this one is describing foot-pounds right here, and then this one goes on to further describe it specifically with torque. So here we have the 1 foot-pound, and it's added the distance of 1 foot to it. So that's what this. Well, I guess this one has a foot as well, but this one is not discussing in terms of torque and rotation. So that's the difference. The distance is in both of them, but this one is applying it to a situation with rotation. Okay. All right. I think this is our final slide, I think, on moments. So a moment can also be considered the result of the forces detouring from a direct line between the point of the loading system and its support. So that's right there in yellow, that detour happening. The blue force is an eccentric force. In order for it to reach the base of the column, it must make a detour. So, okay, coming down, detour. Right, the greater the detour, the greater the moment. All right, we just discussed that. The most efficient structural system, therefore, the big conclusion is to have the least number of detours. Because anytime a moment is created in a system, in a beam, it has to be taken care of as well. We can't just have beams rotating, obviously. So it has to be counterbalanced. It has to be addressed. So it's just by nature more efficient if we don't have to deal with them. If all our loads were coming straight down. Okay. All right. Forces at the supports. So here's a framing plan. So structural systems transfer their loading through a series of elements to the ground. All right. This is accomplished by designing the joining of the elements at their intersections. So here is a cross section through a house. Here's the ridge beam, rafters, bracing struts up in the attic space, Those are our rafters. Then we have ceiling joist, and then down starting at the bottom, going up now, we have our footings, slab on grade, wall, floor, more wall, and then rafters. So if the snow is sitting on the rafters, the load is going to transfer from the rafter to the wall, to the floor, to the wall, to the foundation, to the earth. Okay, that is how we trace the path. Okay, and then these members are joined, and that load, that weight of the snow, has to move from that rafter to that wall. And right there is the where those 2 points are joined, and that load has to be transferred. And a lot of design consideration and money and effort goes into the designing of connections. So that is the force at the support, and that is pushing back, right? So if this wall is not moving, and there's 1,000 pounds of snow sitting up here, and that means that that rafter is collecting that 1,000 pounds and pushing down on this wall with 1,000 pounds of force, and that wall is pushing back up with 1,000. All right, so that's what's happening at the supports. Each connection designed so that it could transfer or support the loading condition. All right, so and then the structure to remain in equilibrium, going back to our very first slide, the supports must apply forces in response to those, which are called reactions. So we have the outside action, which is the snow occurring and pushing, and then the pieces, basically, if we go down to the footing, the reaction is it pushing back. So everything pushes back along the way. The rafter pushes down, that's the action. This wall pushes back, that's the reaction. Then the wall pushes down, that's the action, and this floor pushes back, that's the reaction. Okay? All right, 3 common types of support. So what exactly is happening right there, right at that interface where those two meet? All right, so these are some different types of supports that we'll be looking at. So what exactly happens there? So the 3 big ones are the roller, pins or hinges, and fixed. Okay, and then simple, not so common. The type of support connection determines the type of load that it can resist. Okay, so these are some graphics. They're a little fuzzy, a little rough. Here's the roller. It's on 2 balls, two rollers, 2 kind of cylinder rollers. So 2 rollers there. There's a roller and there's a roller. Okay, so these are the beams, 1, 2, and 3 examples. And these are just graphics for explaining that that's a roller type connection. So something on the weight, something is weighting down on this beam, and then it is pushing down on this roller connection. Okay, so that connection is joining this earth that has that hatch on it, earth or something. I would think that would be the earth. It's typically how we show it. And then we have a beam, and then this is representing the connection between the two, and this is the roller type. Then we have a pin. So we have a circle there, but it's pinned in the middle of a box, and then here we just have a simple triangle. All right, so these are examples of pins. Fixed. So now we just have the beam, cantilever beam, just coming right into that solid wall, and they are fixed. And that looks like a flagpole on the side of a building. Fixed. And here's simple, just sitting right on top of it. Okay? So, now, this is the very, very important part of the matter. The diagram below indicates the forces and or moments which are active and resisted in each type of support. Okay? So, we have objects that are pushing on these or weighting down on these supports, and as we go back to that early slide, and we talked about when Newton's law occurs, either changes are made in geometry or in direction. So things are getting pushed, basically pushed and pulled, and based on what the engineers figure out is going to occur in this particular situation, then they will pick the appropriate type of connection to resist it. So here, this is the roller. It only pushes up and down. That's all it's going to deal with. It's going to allow things to roll. So this is a situation that is used in a bridge, for instance, when we have bridges and outdoor stadium arenas with big massive roofs. They live out in the elements. They experience freezing temperatures and probably temperatures 150 degrees. when it gets so hot on top, directly on a bridge or on a roof. So massive swings in temperature makes things move. And sometimes rollers in situations like that are a good thing because they allow things to expand and contract. So when an engineer wants to allow movement to occur in the vertical direction or in the horizontal direction, then a roller is appropriate. If the engineer doesn't want that movement to occur, they might pick a pin. So this will keep movement from occurring both vertically but horizontally as well. So it's pinned. Fixed connections will stop all types of movement, both the horizontal movement, the vertical movement, and it resists moments as well, the tendency for something to turn. So a roller would just simply allow this beam to move about it. Same with the pin, actually. So it's not going to move left and right, up and down, but it will allow some rotation. All right, so the fixed is the most firm of them all. Simple, frictionless, so that means there's actually no connection. It's just sitting there by gravity, and it's only going to resist this vertical load. Okay, let's just look at a couple examples and we will conclude this first presentation here. So here are fixed, so steel connections. So it prevents all movements and rotations at the point where it is attached to the structure. So here's our fixed, up, down, left, right moments. This thing is not allowed to move in any direction. Okay? Here is a simple connection, not often found in building. So this is a concrete prefab. And so pretty nice looking, nice kind of elegant kind of curves there. So it's just locked in like a jigsaw piece, basically, not connected at all. Okay, and it's just the two. So this is the reaction. This is the connection between the two, right? Where all the force, all the load from above, the snow from above is accumulated here in this middle piece, and then it has to get transferred right there at that support. And then it comes over to the column and gets transferred right here. Okay, not too common though. Pins and hinges. Okay, so here are our pins. All right, so simplest steel to steel connections, lightweight in appearance, not intended to be able to resist bending moments or rotation. So they are allowed to rotate at one point. Joints can move like an actual hinge door, or so that the joint can accept some degree of rotation as a function during the erection process. All right, so let's look at one of these. So there, that's a nice looking pin joint right there. So it has only one bolt and therefore would permit rotation. So it's not rotating now, but it was probably allowed to rotate when it was put up, actually. And it would have been a benefit at that point. So to provide some flexibility. So let's just jump back one more time. So simple steel to steel connection, very light in its appearance. All right, so its connection, everything is happening right there. So the enormous weight from above, and I just gather that it's enormous based on the size of this column. It's coming down. It's going through this plate into these two plates, and then all that energy is transferred right through that bolt into this base plate that's grounded in the earth there, or in the concrete base. All right, so you have to think about that snow load coming down, transfer through the bolt into there. Okay, so that's that. And so not intended to be, so is able to resist, or not able to resist rotation, really. Not designed for that. Okay, so here's some more pin joints, pin connections here on a bridge. A hinge connection, so similar, very similar to a pin, except there are two of them, so not able to rotate. Nice and lightweight. So I would guess that maybe this beam is picking up some weight from above, and then it's moving, or unless it's coming from the column, going out to here, I'm not sure. Or some sort of a lateral stability as well. I'm not sure exactly what it's doing, but whatever direction the flow of forces is traveling, it's going from this plate through those two bolts into this plate. Okay, so right there, a lot of energy is being transferred. And here we see pins right here, right here, right here, right here. And the beautiful Pianos Pompidou Center in Paris. And so maybe not beautiful. Some people say it's actually very ugly. Big kind of convention space, and the guts of the building have all been moved to the outside. So the structural system's outside, the mechanical system, which we can't see, I think it's around the corner there, outside, vertical transportation outside. So kind of all the guts have been moved to the outside, and a brilliant structural engineer on this project with a very kind of articulate structure. See very clearly what's going on there. Numerous pins happening at this large connection. Difference between hinges and pins. The number of bolts that we find in a connection, which infers the ability to rotate. So a hinge has 2, a pin will only have 1. So it will only have a single bolt, as it says there, with enough material to deal with the shear. So you could imagine, just going back one more time, that bolt in there is experiencing shear. So this big connection plate is pushing up, this little connection plate is pushing down, and that bolt is experiencing shear. So that's why we're talking about having to transfer all that shear. The bolt has to do that. Hinge connection will have a greater number of bolts to resist the shear forces. Okay, and here's the roller. All right, maybe I should have moved that up front, but that's the roller. And then so when you're driving under overpasses, you look up and you will see this type of a connection supporting a bridge, very common. So it only, it does not restrain the structure from moving laterally. So it's allowed to move a little bit in this direction, okay? Used to support bridges and spatial structures that experience thermal movements, as I said. Okay, so a lot of information. I hope you enjoyed that. That's just some of the basics we need. The first few lectures are just going to cover some basic concepts and some basic vocabulary so that we could start applying this to broader discussions of buildings. Okay, thank you very much.